So welcome everybody to the Ethics of AI in Healthcare workshop. Thank you all for being here. Today we have a really great lineup of AI scientists, philosophers, and bioethicists, and I'm really delighted to hear what they have to say about this topic. I thought I would start by just giving a brief overview of some of the key concepts, and then maybe raise a question or two that hopefully we'll answer by the end of the day. So, okay. So let me just get started. So artificial intelligence is becoming more and more capable. Here's a picture of IBM's Watson beating two of the best Jeopardy players in the world. I think one of them had won 74 times, and the other one had won over $3.6 million before they lost to Watson. Here's a picture of the Google DeepMind AlphaGo beating the world's best Go player. Until this happened, computer scientists thought that it was going to take maybe another 20 years before this could happen. And then after that, they developed something called AlphaGo Zero, which is sort of based on unsupervised learning, where the machine learning algorithm just learned from scratch the game of AlphaGo, the game of Go, and then the AlphaGo Zero played AlphaGo, the program that beat the world's best player, and it won 100-0, just by learning from scratch. And my kids are chess players, so I have to sort of put in a slide about AlphaZero. So they adapted this unsupervised learning to playing chess. And this program then proceeded to beat the strongest computer program, Stockfish. I think it didn't lose any games. It won about 27 games and drew about 70-some games. So AI's also been adapted to the field of healthcare. Here's a picture of Google's tumor detection algorithm. It's found that sometimes it can diagnose some types of cancers better than doctors. And here's where it's also been used to identify heart rhythm abnormalities, like cardiologists, diagnose various eye diseases as well as ophthalmologists. Is that good? Identify viable embryos as well as fertility specialists. And here's, it can predict suicide. It's better than mental health professionals. And here's a robotic caregiver, which is becoming more prevalent in Japan. I think that they're increasingly using these robotic caregivers because of the aging population. So the promises of AI in clinics, what it promises is improve medical diagnosis, reduce medical errors, eliminate unnecessary medical tests, recommend appropriate treatments, and maybe enable doctors to spend more time with their patients rather than just sort of spending time filling out electronic health records. And then for the broader healthcare profession, there's the promise of being able to lower healthcare costs. I think our healthcare cost is projected to be around $4 trillion by 2020. And what AI can do is sort of maybe eliminate a bunch of the administrative bureaucracies and so on and so forth. It can also contribute to public health. So on the bottom, here's where AI can be leveraged to maybe create individualized diets, not just for people who are diabetics, but also just for everybody, allowing them to live healthier and longer. And finally, AI could also be used to sort of increase drug discovery. So through extracting insights from whole genome sequencing, through human brain analysis, and so on and so forth. They can maybe come up with personalized medicine, next generation of antibiotics, and so on. So this all sounds really great. So what's the catch? I think to see the potential problems with AI, I'm going to just give a brief overview of some of the key concepts of machine learning. There are experts in the audience who are going to say a bit more about this, but this is sort of a quick overview. So machine learning is sort of basically the things that's enabling all these innovations is sort of machine learning, which is sort of a subset of artificial intelligence. And it basically allows algorithms to learn without being explicitly programmed. So it's not rule-based programs. And then within a subset of that is deep learning, where artificial neural networks are adapted, and they can learn from data. Okay. And so usually there's a distinction between supervised learning, which is sort of most common in the healthcare area, where you have some sort of training set. You train, you have certain training set, and then you versus something like unsupervised learning, where there's not structured data. So here's an example. So you train certain algorithms to recognize apples. And then you have, then you sort of show the algorithm something like an apple, and then it tells you that it's an apple. And in the cases of unsupervised learning, you just have a bunch of input data, and then it'll kind of sort of cluster and sort of sort itself into apples and bananas. And then there's something called reinforcement learning, which is basically just learning through trial and error. Algorithm will be rewarded if it gets something right. So it's mostly used in games right now, for example. So here's a toy example of the dinosaur trying to get to the tree, and it'll get rewarded by getting to the tree and sort of punished if it didn't get to the tree. So, okay. And then there's something, and this is deep learning. So it's using basically, it uses sort of different layers of hidden layers to look at, for example, different pixel values, the edges, and so on of a picture, right? And then from the layers, it then sort of gives you some, it sort of then tells you that it's a dog that it's looking at. Okay. So what are some of the problems with machine learning? Well, machine learning typically requires a lot of data, so the algorithms are only as good as the data. So one problem is, it's a very well-known problem, is the garbage in, garbage out problem. So if you have very bad data, then even if your model is really good, you're going to get bad results. So, so here's an example in healthcare where the data, mostly the subjects sort of in clinical trials are male subjects. And so that means that a lot of the drugs, it's not clear that they work for, say, women. And so that's a big problem in clinical research trials. And it gets compounded when you put the same data into machine learning. So here's another example. So you can have perfect data, but if your model is not very good, then you also get bad results, right? So machine learning can fail to identify a pattern even when there's a pattern there. So that's the underfitting problem, right? It can also overfit. So it can identify a pattern even if there isn't one. So if you give the machine a lot of data, it might just try to give you a pattern even though there isn't one. So, okay. And this is all exacerbated by the black box nature of machine learning, especially deep learning. So here's where, when you use deep learning, there's a bunch of hidden layer networks, right? And so, so it's very hard to figure out, it's very hard to interpret right? Know what exactly is going on, like how the machine is learning, which layer it's looking at. It's sort of looking at different pixels, et cetera, et cetera. It's very hard to figure out how it reaches its output, its decision. And so that raises questions of interpretability, explainability, and trustworthiness in sort of the machine learning. So I really like this picture. This is your machine learning system. Yup. You pour data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Well, just stir the pile until they start looking right. So this is not too far from what's going on sometimes. Okay. So some people are attempting sort of technical solutions to this black box problem. So here's one solution that some machine learning scientists have suggested, which is to add an additional layer to interpret what the black box is doing. So a question I have about this is just that, how can we be sure that the post hoc explanations provided are the reasons why a model gave the results that it did? And if these aren't the reasons, what is the value of these explanations? And maybe there's a way to test this. So if these are, in fact, the reasons why a model gave the results that it did, then the model, this sort of interpretability model, should be able to give the same results as the black box model when applied to a given data set. But if it can do that, then this raises the question of why you need the black box model, or whether you need it anymore. Okay, so I'd be interested in hearing what the AI scientists have to say about this. Other people have suggested that maybe we should care more about accuracy. So there's a trade-off between, there seems to be a trade-off between interpretability and accuracy. And so some people have suggested that maybe we should just care about accuracy, especially in the field of medicine. So Alex, for example, is a proponent of this view. And his reason is that medicine may not all be all that interpretable either. So a lot of medicine, it's kind of trial and error. We don't exactly know the causal nature of the medicine, and so on and so forth. So I have some questions about this. So it seems like that sounds kind of right, but it seems that maybe we still know a bit more about how medicine works in terms of its causality and its nature than we do about the black box nature of algorithms. And another question I have is whether we can be sure that a deep learning model is accurate, isn't accurate in a particular case only because it got lucky. After all, we know that deep learning image classifiers can be vulnerable to, for example, something like a one pixel attack. So here's an example of the one pixel attack. So if you look at the top, that's supposed to be a ship, but the algorithm, just by changing one pixel, classifies it as a car, right? And it'll take this one, it's a deer, and it classifies it as a dog just by changing one pixel. So this is sort of known as the one pixel attack. So it says, 86.4% that it's a dog. And so if deep learning models can be vulnerable to one pixel attacks, can they be even more vulnerable to multi-pixel attacks or gradient attacks? So that's something that is important if it's going to work in the in healthcare, right? So just imagine these radiology sort of images. We need to be sure that they're not being attacked in this kind of way. So let me just say two other things. So I've been describing machine learning, sort of ethical issues when machine learning isn't working all that well, when the data's not good or when the algorithms aren't good. But there are also ethical issues that arise when the machine learning is working perfectly, right? And so here's one example. So I mentioned earlier that machine learning might be able to help us diagnose cancer, maybe someday discover drugs that will cure cancer, or give us or can give us better individualized diet so that we can live longer. So a philosophical and ethical question is whether living longer is living better, right? So now if we got a lot of people, like do we, should we prioritize life extension over, say, life replacement, right? Given sort of the constraints of resources on this planet and so on and so forth. So that's a philosophical question. It's a well-known problem, but it's something that we'll have to think about in the context of machine learning as well. And here's just another example. So earlier I mentioned that we can use we can use machine learning to figure out which embryo is going to be more viable. You can imagine that process gets perfected, and now we face the question of whether we should be having designer babies, right? And again, a very well-known problem, but so these are just some examples, and there are many more. Okay, and then just one last thought. Currently, many devices that make use of machine learning algorithms are either rolled out without extensive testing, or they're kind of tested in the wild, so to speak. And such devices can affect people's well-being in quite negative ways. So here's an example of a self-driving car crashing in Arizona. So in the case of drug development, drugs are only put on the market after passing several stages of clinical trials. Is it worth thinking about having something similar to regulate machine learning algorithms that have the potential to affect people's well-being? Okay, so those are just some introductory remarks. I'm really excited about the conversation to follow. And first of all, I want to introduce Francesca Rossi, who is our next speaker. She's the IBM AI Ethics Global Leader, a distinguished research scientist at the IBM T.J. Watson Research Center, and a professor of computer science at the University of Padova, Italy. She's published over 190 articles and edited many volumes, and she's a leader in this field. And let's welcome Dr. Rossi. Thank you.